I'm currently teaching an algebra-based physics course, and we have to do things like the electric field due to point charges. That's fine. Electric field due to parallel plates. Well, here's the equation, right? And it's constant. But other than that, they can't derive it. Now there are ways to derive it. You could use Gauss's law, you could use integration, but this is algebra based, and even Gauss's law I think is a little bit of a stretch. So but we do need a parallel plate capacitor, right? So we need to know that if you have two plates that are parallel, and one plate has a charge plus Q and the other has a charge minus Q, then there's three important things about this. Number one, the electric field inside the plate is constant. Actually, be a constant. That's a vector. I can't have a vector equal to a scalar, right? So vector, vector. E inside is a constant. Also, E outside is 0 newtons per coulomb. There, I'd just like to be right. And finally, the magnitude of the electric field inside doesn't really depend on well, it depends on the charge density, but we can write it as the total charge of one plate divided by epsilon naught times the area of one plate. And so we can't derive that, without calculus or Gauss's law. So instead, I want to show that with point charges. So imagine that I draw this from the side. Let's do a 2D capacitor. And I have 1, 2, 3, 4, 1, 2, 3, 4. 4 charges on each side, and it doesn't matter if there's wires. And I want to show that and there's actually way more because it has to be in 3D. It can't work in 2D. If I have a finite number of charges on these plates, I can calculate the electric field at any location. Let's call this the origin. So this is the vector RO, right? The vector RO. I should have drawn this bigger. Let's draw it bigger. We got more paper. Okay, so here's my large capacitor, plus, 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 minus, 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 minus. And here's my observations. I'm going to put it over here. RO. That's where I want to find the electric field. Well, since point charges, the electric field obeys the superposition principle, I can find the electric field due to this, plus this, plus this. So for that particular one, let's call that R1, and this will be R. That's the vector from the point to the observation location. If that's the case, then I can calculate that one particular electric field. I'm going to call it dE, because it's just part of the total electric field. K times dQ, because that's just dQ, 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 divided by the magnitude of this vector, magnitude R squared, times R hat, which is a unit vector in the direction of that. And then I do the same thing for this one. So I get this electric field, that one, oh, these are smaller, that one. And then over here I do the same thing. These are going to be pointing towards it because in this case, DQ, all the DQs are negative. So this will be just, like that, that. And then you add up all those vectors and then you can do it wherever you want. And so that's what we're going to do. Now, I want to put a finite number of points on two plates. And I'm going to model it in 3D. I'm going to draw these arrows in 3D. It's going to be great. Now, I could neatly arrange. I could have it looking at the plate from the side. I could say, okay, I want 1,000 points, and it's going to put them evenly spaced. But I'm not going to do that because that's boring. Instead, I'm going to do this. I'm just going to put them at random locations, random places on the plate. And if I have enough random ones, it's kind of the same as uniform. And it's just more fun. Okay. So let's get to it. Jumping to Python, we're going to do some coding. We're going to make this happen. I do need to pick some values for the stuff, but we can do that. Okay, so I'm in Python. I've already put my K value. I got a head start, and I apologize. I was so excited. I'm going to start this before everyone else. Let's make that a little bit bigger. Okay, that's good. So there's my Coulomb constant. I'm not going to put the units in there. That's 1 over 4 pi epsilon naught. I need my total charge on one side. I'm going to say, I'm picking a micro Coulomb. I don't even know if that's going to work. It's not going to matter because we're going to scale everything. We're going to draw the vectors. We're going to scale the vectors, so it's going to be fine. Now my number of points, let's start with something small like 100. I always like to start off with a manageable number, and then we can always make it bigger. One of the ways I like to count in WebVPython is to have a counter n equals 0. There's other ways to do it, and you should do it your way. The end. Okay, what else do I need? The separation between the plates, D, I'm going to put 0.02, 2 centimeters. I'm going to make them big plates, so they're L by L, which is 10 centimeters. So they're, they're big plates. I don't know. It doesn't really matter how big they are because you can change it. Okay, so now I need dq, the charge of each point, right? Q is the total charge on the plate. So dq is going to be Q divided by N. Yeah. Now I'm going to just draw. I'm going to draw 2 plates. They're not the charges. They're just plates so we can see them. So let's call this left plate. It's a box, and it's going to be centered on the origin in the x direction. So the position is going to be vector negative d over 2, 0, 0. That's the center of that box. Now the size is going to be a vector in the x direction. I'm going to use, let's see, I picked a d over 50. So it's going to be d over 50. And then L. Yeah. And let's just leave it as gray. And now I'm going to copy this. And I'm going to make my right plate. And that's, I'm going to paste it. It's the same thing, right? Except that it's plus d over 2. Okay, let's run that and see what it looks like. And so there's my 2 parallel plates. And I can rotate it around. And I'm going to create the electric field inside there. And that's what I'm going to do. Maybe we might help to make them spread out more. I don't really know. Let's just see. Okay. Going back to edit. Now, I do want to do this. Let's make them opacity equals 0.3. Opacity equals 0.3. That'll make them a little transparent so that when we put charges in there, we can see them a little bit better. There. They're see-through. See? Okay. Now let's just practice drawing all the points. So I want to make 100 points on each side. So let's do this. While n is less than n, n equals n plus 1. I always add this n equals n plus 1. Because if you don't increase the value of n, then the loop will run forever, and that's Python jail. You get put in Python jail. No one likes to be put in Python jail. So I like to put that there. Now, what I'm going to do is create a set of random vector points for the left plate and then one for the right plate. So let's call this RT1. That's my temporary random vector for the left plate. And it's going to be equal to a vector. And I'm going to have its x value is going to be negative d over 2. It's on the plate. But then the y value is going to be between negative L over 2 and positive L over 2, and the z value between negative L over 2 and positive L over 2. So I'm going to put the vector negative d over 2. That's my x coordinate. And then my y coordinate, I'm going to use the random number. And in Python, in WebVPython, really we only have random, which returns a number between 0 and 1. So I need to do a little trick. Let's do this. I'll write it and then explain it. 0.5 times L, that's L over 2, times random 2, actually, no, times 2 times random minus 1, comma. Okay, so 2 times random gives you a number between 0 and 2. And then if I subtract 1, I get a number between 1 and negative 1. And then I multiply that by L over 2. So now I have a number between negative L over 2 and L over 2. Done. I'm going to do the same thing for the z direction, so I'm just going to copy this. There. And now it should work. Now, let's go ahead and use that random vector and just put a sphere there. And I'm only going to do the left side. So let's say sphere. I'm not going to give it a name because I don't really care about it. And you can't even see that. Sorry. How about that? Sphere, position equals that vector that I just created, RT1. Radius is going to be equal to, let's put D over 20. And then let's make this the positive side. So the positive is going to be red. Color equals color dot red. And now we can run it. Let's just see what happens. Okay, there we go. 100 points on that left sphere. You see how they're randomly distributed, and that's only 100. I can do 1,000 or 10,000 very easily, but let's just leave it at 100 right now. I want to go over here and do the same thing for the. I'm going to copy this, and I'm going to make a variable for the right plate, and I'm going to call it. Maybe I should call it RT1, 2. That makes sense. And this is going to be plus D over 2. But other than that, it's exactly the same. And then I can make another sphere. I keep putting this thing down. I don't know why. So maybe this is scrolls. No. Okay, that's fine. Sphere position equals RT2. Radius is the same. D divided by 20. We don't even need to draw these spheres, just so you know. And then color, they're blue, they're red, they're negative, so they're going to be blue. Color equals color dot blue. And that's that. So I'm making my spheres. Let's see if that works. Okay, so there's my charges on my parallel plate. And we're going to ramp that up in a little bit. I'm going to need to go through and calculate the vector from each location, each one of these point charges. I'm going to need to do it for multiple locations. So I need to know where all these charges are. In this loop, it just goes through and makes the variable and just throws it away. Okay, so what I'm going to do is to make a list of charges, and they're just vector locations. So I'm going to make the left plate, I'm going to call it LQ, and it's an empty list. And then RQ is an empty list. So the right charges and the left charges. And then I'm just going to add those values, those vector values to my list. So LQ equals LQ plus square bracket RT1. And you can do append for lists if you want. I like this because it's the way we do all the other updates and stuff like that. So, but you do it your way. RQ is RQ plus RT2. So now I'm going to have a list of all these points. If I want to print them out, you could, and you can see what it looks like. Ooh, that was a bad mistake. So let's just run that and then print RT1. It's going to be crazy because it's 100 things, but it's not that bad. Just to see how, no, not RT1. LQ, left plate. And it should be a bunch of vectors. And there they are. And they all have the same X value, negative D over 2. So it is working. So yay. Okay. Let's get rid of the print. Now what I want to do is, I'm going to put observation locations at different places and calculate the electric field. And so I'm going to do that a whole bunch of times. So since every electric field deals with every point in every list, I'm just going to make a function. And this is the perfect place for a function. So let's define a function. I'm going to call it E because that's awesome. And you could just use LQ and RQ as a global variable and just pass the location. But I'm not going to. I'm going to say E. I don't know why. I should. I'm going to give it a, let's see. I used the observation location. Let's just call it ROT for temporary observation location. I want to have the same thing twice. And then I'm going to pass it the two lists. Let's call it QL and QR. Those are my two lists of charges on the left and the right plate. And I like to put something in here, takes location and lists of charges, returns total electric field. Because one day I may come back and look at this and say, what the heck did I do? So I need to go through every charge in that list and calculate the electric field in both lists. So let's start with the left side. So I'm going to, every time I have a charge, I'm going to calculate the electric field and add it to the total. That means I have to start with something. I have to start with a zero total. So I'm going to say ET, the temporary electric field, is vector 0, 0, 0. I can't add to something I don't have. I have to start with that. Now I'm going to go through all the charges in LQ. So I'm going to say for R1 in QL. And this is a great way to progress through a list. Every item is just called R1 at a time. I'm going to say the first one's R1, then the second one. So it's a great way to traverse. And I can just call it R1. It's just a vector. Now I just need to calculate the vector from R1, whatever that is, to my observation location. So I'm going to call that RTT for temp R. And that's just RO, ROT, the observation location, minus R1. Now I can calculate the electric field. I'm going to call it dE, just like it did on the paper. And it's going to be equal to K times dQ times norm RTT divided by mag RTT squared. Now I need to add that to my total. ET equals ET plus dE. And that's it. Okay, now I'm going to need to do it again. Let's just copy this. I need to do it again for the other list. And that don't like that. I'm going to say R2 in QR, the right list. And this is the same. That should be 2. Should be negative, right? Because now on the right side, the charges are negative. So I'm just going to add a negative sign in there. And that should be it. And let's return ET. Now let's just try this and see if it works. Yeah. So let's say RO is vector 0, 0, 0. Print E equals E R0. And let's put the units, newtons per coulomb, done. So this will see if I should get a value. It should be in the positive x direction somewhat, 'cause it's dealing with random numbers, but that's fine. There's my charges, and it didn't work. Ooh, what's that? Undefined is not an object. Okay, good thing we tested. Okay, def E, rot, ET. RT, RO. Let's just print. Let's see if print RO. I don't know. They'll tell me if I'm having a problem with the function or not. This is print RO. Don't need to do that. Oh, it did that. Okay. So there's a problem in my function. What is the problem in my function? RQL, RQ, colon, ET, for R1 in QL, RTT, RO minus R1, DE, DQ, norm RTT, mag RTT squared, ET, that's fine, R2, DE. Huh. That's weird. Maybe my list is bad. LQ equals LQ plus RT1. I think that's fine. Let's just try. Let's see. Actually, I had another version of this. Let's just try. When in doubt, use your backup. I did do this before. You know I do that. Let's run it like this. Let's see if that works. Undefined is not an object. Evaluating insert symbol iterator. Okay, let's just replace this part. I promise you it works. Huh. What the heck? Oops. I messed up big time there. See what happens when you just try to do things live? Oh, it logged me out. That's weird. Let's see how much of it saved. I feel like it didn't save anything. Okay, well, I got the main program down. So I'm going to go ahead and copy my other version and see. And I'll just go through the whole thing. That's fine. I think you've got the whole point down. I'm gonna copy this whole thing. Copy. And then I'm gonna create a new program. I'm positive I saved it. Good thing I did it beforehand, huh? Okay, so there's the whole program. I do need to get rid of my other, that shouldn't be in there twice. Let's see if this runs. Okay, it's working. See? Ta-da! Okay, so look, I'm going to show you the result here because it is kind of cool. I have a bunch of electric fields inside of there, and this is for, I think, 1,000 points. I also calculated the electric field outside. Now, I haven't done everything because I didn't show the magnitude electric field. I need to do that. But you can see here, zooming in, all these arrows are pretty much the same length and in the same direction. And this is with random numbers, so it is working very well, and I'm very happy with this. We'll give you the code. Let's save this. E-field parallel plates. So there are a couple tricks here. Number one, my number one trick is right here, E-scale. So I'm making the vector for the arrow as the electric field. But the electric field is going to be huge if I draw it. So I need to have some scaling factors so that it looks better. In this case, I want them very small, so my electric scale, E-scale, is very small. All this other stuff we already did. I already did this function. I'm not even sure what I did wrong, but it was, the idea was right for sure. Now, in order to go on the inside, I actually have a double loop. So I start with my observation location at the bottom corner of the thing, and I'm going to move up one piece, a DR, until I get to the top, and then I'm going to repeat it and just move over one in the Z direction and keep going up. So here's I'm starting at that's my bottom lower left of the plate. This is my first move. It's I make 1/10 of the way. And so this loop moves in the Y direction. And so each time I move the observation location, I calculate the electric field for all the points, and then I plot that and put an arrow there. And you see there, that's at E temp, which I just calculated, scale, color yellow. And then I move my Y value up and repeat that. And then once I'm done, I go up here and move my Y value back to negative Y over 2, and then increase my Z value by this line right there. And that's that. Now this is the same thing, except that I moved all my points outside the capacitor on the right side. You could do it on the left side too, but I didn't really care about that. So there we go. And then if you run it, it does look, every time you run it, it's going to look a little bit differently. You do not have to have all those charges in there if it slows down too much. I can just comment out the charge, the sphere part, and it won't put them. But it looks pretty good. I'm pretty happy. And you see, these outside electric fields are very, very small compared to the inside, and that's pretty cool. So let's print out the electric field and I didn't do a perfect job because I've only done it exactly in the middle. I could move this over I could do it again over here, but it's going to get too messy. I'm pretty happy with the way this looks. I do want to do one thing. I've shown that the electric field's constant on the inside. I've shown that it's very close to 0 on the outside. Now I just need to calculate the magnitude inside. So I'm thinking I could do starting from one side of the plate and just moving across, plotting the magnitude electric field and show that it's constant. That'd be kind of fun, but I'm not going to make a graph. I just want to calculate that. So let's go down here at the very end. Oops. My computer skills are very poor today. Okay. Down here. I'm going to say print at R equals 0. E equals E vector 0, 0, 0. That's at the origin. And then I need to give it those two lists, which are LQ, RQ. And then I'll put the units, newtons per coulomb. Now let's calculate the theoretical. So in this case, I need epsilon naught. So just a quick note here, 1 over 4 pi epsilon naught is equal to k. So let me switch to the paper because I always make a mistake here. So let me write this out. So 1 over 4 pi epsilon naught is equal to k. So 1 over k equals 4 pi epsilon naught. So epsilon naught is going to be 1 over 4 pi k. Okay. Switching back. So I'll call it ep is, what did I just say? 1 divided by 4 times pi times k. And E theory equals Q divided by L squared ep times L squared, which is the area. Print E theory equals E theory newtons per coulomb. And let's see how that works. If that works, if they're close, we win. Okay. So actually they are, right? So these numbers look very different. This is the actual electric field, 9 times 10 to the 6th in the positive x direction. In the y direction, it's 100 times smaller. In the z direction, it's 10 times smaller. Almost close to 100. So it's small. And that's just 1,000 points. We can fix this. So this is very close to 1 times 10 to the 7th, and that's 1 times 10 to the 7th. So it's close enough. Let's just increase the value of points and see if we can make it a little bit better. So up here, I'm going to turn off the spheres, like I said, and I have 1,000 points. What about 10,000? If you can do 1,000, you can do 10,000. So let's do 10,000. I may have just made a mistake. Okay, it did it. That's pretty nice. Very uniform and orderly electric fields. And again, it's about the same. I'm kind of surprised, but it's still close. I'm still happy. Okay, that's it. Electric field, parallel plate capacitor for fun. I'm going to put a link to the code down below. You can manipulate it as you like and have fun with it.